Have you ever stopped to think about the hidden logic that kind of organizes our entire world? I mean, from something as simple as making breakfast to building a massive skyscraper, there's this fundamental set of rules that dictates the order of everything. Today, we're going to pull back that curtain. It all starts with a question we don't even have to think about: socks or shoes first? The answer is just obvious, right? You can't put on your shoes until you've put on your socks. That simple choice, it's all based on a dependency. And believe it or not, that exact same simple logic is what lets us manage these unbelievably complex projects with thousands, even millions of interconnected steps. The real challenge is, how do you map out all those dependencies so that everything happens in the right order?
So that brings us to the core of what we're talking about today, the dependency puzzle. How do you figure out a valid sequence for a whole bunch of tasks when some of them absolutely have to be completed before others can even start?
See, this isn't just a simple to-do list where you can do things in any order. It's more like a complex, tangled web. In a spreadsheet, you change one cell and it can set off this whole cascade of updates. In software, you can't compile one module until another one is ready. And you're definitely not putting up walls on a construction site without a foundation first. Every single connection in this web is a rule that says this, then that. So how do people, computer scientists, project managers, how do they visualize this web? Well, they use this really elegant mathematical tool that was designed for exactly this purpose: the directed acyclic graph, or what we're going to call a DAG. I know, that sounds super technical, but don't worry, we're going to break it right down. A DAG is really just a map. It's a map of tasks and the dependencies between them. It's got vertices, those are the tasks, and edges, which are the one-way connections. Let's look at each part. Okay, first, the graph part. Just think of it as a network. The dots, or the vertices, they just represent the individual tasks you need to get done. The lines connecting them, those just show the relationships between the tasks. Simple as that. Next up, directed. This is important. It means all the connections are one-way streets. The arrow on the line shows you the flow. So, if an edge points from task A to task B, it means A must be done before B. There's no going backwards. And this brings us to the most crucial part of the whole thing: acyclic. It just means without cycles. You can never, ever follow the arrows along a path and end up back where you started. I mean, just imagine if task A depended on task B, but task B also depended on task A. Where would you even begin? You can't. It's impossible. And this quote right here just nails it. A circular dependency creates this logical trap, a paradox with no valid starting point. It makes scheduling things completely impossible. That's why, for any system of tasks to actually be solvable, it has to be acyclic. No exceptions. Okay, so we have our map now, the DAG. But a map isn't a plan, right? So how do we take this web of dependencies and turn it into a single, straight, step-by-step to-do list? Well, the answer lies in a process called topological sorting. Think of a topological sort as the magic trick that takes our DAG and produces a valid sequence of events. It's the algorithm that guarantees that for any dependency, like our socks before shoes, the prerequisite task will always show up earlier in the final list. It turns that complex web into a simple, actionable path forward. So how does it actually work? Well, one of the most intuitive ways is an algorithm called Kahn's algorithm. It's pretty straightforward. The algorithm just scans the graph and looks for any task that has no incoming arrows. A task with zero prerequisites. Let's say it finds task A. Great. You add task A to your final sorted list. Then you basically just erase it and all its outgoing arrows from the graph. And what happens? Well, that might reveal a new task, maybe task B, that now has no incoming arrows. So you add B to the list and you just repeat the process. You just keep plucking off the ready tasks until your list is complete. So this brings up a really fascinating question. If you run a topological sort on a graph, are you always going to get the exact same to-do list? I mean, is there only one single correct order? And the answer, maybe surprisingly, is often no. Take a look at this example. Task 3 has to happen first, and Task 2 has to be dead last. But once you finish Task 3, both Task 1 and Task 4 are totally ready to go. Neither one depends on the other. So you could do 1 then 4, or you could do 4 then 1. Both of those are perfectly valid sorted lists. So here's the key takeaway on that. A unique, one and only one order only exists if the graph is a single, unbroken chain of dependencies. The moment you have a choice, a point where 2 or more tasks are ready to go, like task 1 and 4 in that last example, well, that's when multiple valid orders become possible. It's those choice points that give you flexibility. All right, so now that we've got the theory down, let's talk about where this powerful idea is hiding out in the real world. Because trust me, it's the invisible engine behind so many of the tools we use every single day.
I mean, you will find this stuff everywhere. Project management software uses it to schedule milestones. In software development, it decides the right order to compile code. When you change a cell in a spreadsheet, it figures out which other cells need to update first. When you install a new app, it's resolving all the library dependencies in the background. Even a university course catalog uses it to make sure you've taken the right prerequisites before you sign up for a class.
Let's zoom in on project management for a second, specifically a technique called PERT. It's a little different here. In this kind of model, the dots, the vertices, they aren't the tasks themselves. They're the milestones, like foundation poured or framework approved. The lines connecting them, the edges, those are the actual tasks, and they're usually labeled with how long they'll take. Now, by mapping out a project this way, managers can find the longest path through the graph, from the very start to the very end. And notice in this example, the total time isn't just adding up all the tasks. It's the longest chain of dependent tasks that actually determines how long the whole project will take. And that longest path has a special name. It's called the critical path. It's the sequence of tasks that has absolutely zero slack, zero wiggle room. For a business, this is a huge insight. It tells you exactly where you need to focus your resources to avoid delays. Any task that's not on the critical path can be delayed a little without hurting the deadline. But a one-day delay on this path, that means a one-day delay for the entire project. It's absolutely key to managing risk. So, wow, we've gone all the way from socks and shoes to complex project timelines. Let's just wrap this all up and talk about why this concept really, truly matters. At the end of the day, DAGs and topological sorting aren't just some abstract thing for computer scientists. They're a formal language, a system we've developed to understand, map, and execute tasks in a logical order. They really are the blueprint for efficiency, letting us build software, manage enormous projects, and process data in the most effective way possible. And that brings us to our final thought. From the way your phone boots up its apps to the sequence of traffic lights on your commute, our world is built on this hidden network of dependencies. So the next time you see some complex process just unfold seamlessly, maybe ask yourself, what hidden dependencies are shaping your world right now?